The IOBs contain a wealth of technology, as I mentioned in a previous REL, but the newest resource is the SERDES functionality. The SERDES resources offer the ability to encode or decode a signal with dedicated serializer-deserializer logic that is embedded in specific IOBs. This functionality, by its complex nature, offers many options to customize. To make it easier, Xilinx offers two places for designers to customize their SERDES pins. The MIG, or Memory Interface Generator, and the ChipSync Wizard are used for this purpose. The MIG, of course, builds custom memory controllers, but if a designer only needs to customize the SERDES functionality, he can use the ChipSync Wizard. Besides the SERDES functionality, each I/O pin can be programmed to communicate with over 40 different I/O standards, including some differential I/O standards. This programmability improves performance significantly. If you're going to select an I/O standard, you can use the PinAhead pin assignment utility and add the appropriate assignment in your design's UCF file, or specify the standard with your synthesis tool, either through the synthesis tool's constraints tool or through an attribute in your HDL. This is a screenshot of PinAhead. This tool allows designers to lay their pins out and study the implications of their pin assignments. This tool has a design rule checker that helps determine if they are violating any of the I/O banking rules. It also can provide a WASO analysis to see if the layout runs a greater risk of suffering from ground bounce due to an inefficient pin layout. Of course, PinAhead lets you see both a package and pin view of your design and makes it easy to make pin assignments and pin attributes. This slide is intended to show you how many features Virtex 5 has that lend itself to source-synchronous memory applications. As I mentioned earlier, the SERDES functionality is easily added to your design when you use the MIG or ChipSync. Virtex 5 also supports the routing of the decoded SERDES clocks to neighboring I/O pins through the regional clock and I/O clock resources. The block RAM also has embedded error correcting code logic, or ECC logic, embedded in each dedicated block. The MIG supports a wide range of memory controllers, including DDR2 and QDR standards. Finally, the Excite feature allows you to remove the termination resistor you usually place outside your FPGA with a programmable impedance that is electronically duplicated on each I/O pin in that bank. This is supported through a number of I/O standards and simply requires you to select the appropriate I/O standard and then place a couple of resistors per I/O bank. This slide shows you a little bit about how the ISERDES functionality is embedded in specific pins. Input SERDES configurations allow for division of the input high-speed signal by up to 10-bit width. The ISERDES also includes a dedicated bit alignment resource, word alignment, clock alignment, and dynamic phase alignment for each of these pins. And this is all done without using any FPGA fabric. All of this is dedicated in some, but not all, I/O pins in the device. Similarly, output SERDES configurations allow you to multiply by up to a 10-bit encode. A 3-state implementation is also supported because of the dedicated tri-state buffers associated with each I/O pin in the device. This makes the resource ideal for memory applications. And as I mentioned earlier, the ChipSync Wizard allows you to customize your SERDES resources. ChipSync gives the user complete control over the SERDES programmability on a pin-by-pin basis. ChipSync provides an instantiation template and a netlist for the particular SERDES interface you're designing. It is optimized for a variety of I/O standards, which makes its output reliable as well as quick and easy to use. In summary, your ASIC design is going to need some optimization to whichever FPGA you choose. The problem is that today's FPGAs have so much dedicated hardware logic that synthesis tools just cannot support inference for all of their functionality. In fact, one of your challenges will be to instantiate the resources you need for your design. To aid in optimizing your design, Xilinx provides the Architecture Wizard and the Core Generator utilities to speed up your design conversion. However, if you want to infer resources, most architectural resources are inferable in some form. The additional challenge will be for you to know the limits of your synthesis tool, what attributes you might have to assign, and if there is any particular coding style that is required. Finally, we started our 10-step guide to design conversion, and we got through the first 3. And we'll continue with this list in our next REL. Well, there are lots of places to learn more about FPGAs, and they all start at support.xilinx.com. One of the best software manuals to use is the Synthesis and Simulation Design Guide that is available online. This provides general recommendations for coding practices and specific tips for coding for particular FPGA device families. I also want to point out that the Virtex 5 User Guide contains additional useful information about the SERDES and clocking resources. You may want to refer to these documents to learn more. In fact, I had to. I would also like to mention again that there are 2 basic FPGA architecture modules that discuss the basics of the Virtex 5 architecture. You may find this useful, especially if you want to learn more about the clocking resources. Likewise, there is an REL that provides more information about the Architecture Wizard and the options that can be selected for optimizing clocking resources. Both of these, I'm sure, will be useful, and best of all, they are free. Now, don't forget to take Part 2. This will continue the ASIC to FPGA coding conversion discussion. Again, my name is Frank Nelson. You've been listening to Part 1 of the ASIC to FPGA coding conversion RELs. Thanks for listening.